Okay, fasten your seatbelts. You're about to experience one of the most fascinating subjects of geospatial analysis. GIS data. So if this is a review for you, don't check out. The goal is to review these important topics and make sure you're really comfortable with the nuances of vector versus raster data. Think about the applications to your analyses, to data organization, tool selection, database management, and most important, think about uncertainty as we review these topics. There are only a few truly fundamental topics that you need to understand: data nuances and how to map locations accurately. The rest is pretty much frosting. Okay, so this is the fundamental knowledge you need for building appropriate GIS. Projects that are fit for purpose, and data that's fit for purpose. You need to know what each type of data is that you're dealing with to determine what you can do with it. Don't fall asleep on me, because it is geeky fun. It really is. The more you get to know this stuff and learn this stuff and understand it, it's worth it. Just hang in there. Okay, so even if this is not new to you, if it's new to you, here's where we're going to start. There are basically two spatial data types, right? And that's what I want to go through in this first set of lectures. They're structured differently, they behave differently, you manipulate them differently, and you have to connect and store the databases or attributes to them differently. So what are we talking about? Okay, here on Earth we have features, we have places, we have things like phone booths, and we can measure where they are, and we can collect information about the feature and then connect the data about the feature to the location. And voila, that's spatial data. We have features, we can map their locations, we can collect information about them and connect this database to the map. That's GIS. Well, that's the first part of GIS. But what should GIS data represent? It could represent anything in the whole world. But because the world is infinitely complex and computers aren't, we have to start making decisions. So before we get into the weeds, we need to think about what kind of simplifications have to be made. We have to make choices when representing the real world. Assumptions are made. How much detail? What spatial scale are we going to work at? How complete should the data set be? Like in this example, we've got 3 different scales of a stream network. One is so coarse you can't even see it on this extent of the map. The purple is the finest scale. It's digitized or created at a scale of 1 to 24,000, which is similar to your USGS quad maps, your topo maps. A coarser scale is 1 to 100,000, where depending on how the size of the map is set up on your computer, 1 inch on the screen would equal 100 inches on the ground, that kind of a thing. And you can see the simplification that takes place, right? But also, are we collecting information about whether the streams are ephemeral? Are they naturally occurring? Are they canals, man-made? You can see that there are a lot of streams here that don't connect, so there are issues with the data. I want you to think about how we're representing the real world with spatial data. And I need you to be curious about the lineage, the age, how it was created, what potential is there for error, what kind of generalizations have been made. We're moving beyond just accepting data at its face value here. Whether you're new to GIS or not, I'm trusting that you have seen spatial data before, right? Whether it's a search for a secondhand bookstore in your neighborhood or looking at a weather map, we have all seen spatial data before. But my goal is to make sure that you really appreciate and understand what spatial data is and where it comes from, and to interject a healthy level of skepticism into your analyses and your workflow. You can't just take it at face value. So, in GIS, we add data to a map. Here we've got points marking cities, we've got roads, it looks like, and we've got some kind of a base map. The purple looks like Huck 4 watersheds. So there's a lot of different layers going on here. We move it around, we change the colors, we sort the attributes, calculate areas and lengths, and generally trust that it's reliable and trustworthy information, both coming in and going out of your analyses. Yeah, I think that's enough there. But this is what the data actually represents, right? If you were working with a land cover data set, this is what it would be mapping. This is an infinitely complex surface that has to be synthesized to a grid or a matrix of single valued cells, or pixels if you prefer. So you have to decide what level of detail is being assumed appropriate for representing the land cover of the surface. How is all of this complexity going to be simplified? And what methods were used to simplify this information? For example, are the trees being mapped with points, or if we talk about that matrix of cells, how are the trees being represented? Is it just kind of binary, true, false, grass versus trees? Are we able to collect information about tree species? How about tree height or tree health? And then how precise is the boundary between forest and not forest being mapped? You can see that there are a lot of choices that have to go into how we're going to map this really complex world that we live in. Here's an example showing streams and lakes in Minnesota. And you can see that this is a really complicated landscape. Big wetland areas that probably change a lot over the course of the year. We've got streams running in and out of wet areas, of open water, and maybe sometimes open water. So where would you draw the boundary of a feature like this? You know, we have some things that may actually be defined as ponds, but what's the difference between a wide section of river and a stream network? How would you go about mapping this? This is the lake body data set that I got from the state of Minnesota. And you can see that only some of these features have been identified and mapped. They haven't been, the outlines don't necessarily match what we see in the aerial photo, so there's a temporal issue that's going on there. And then it looks like the mapping was done at two different times or at two different scales. Here we've got this very coarse, generic thing that encompasses a bunch of little pond chains, and then other features that are completely left. More detail went into digitizing the boundaries of these lake features. So, what does that mean? How would you even know this unless you looked really closely? How would you know to be suspicious of this data and realize there were so many features missing? Okay, and then here's another interesting example. It's showing both water bodies and streams. Who's responsible for quality checking this data? Is it the person producing it, or is it the person using it? What is a water body and what isn't? And then the different colors of streams. So let me show you this GIF that I recorded. The purple, this pinkish purple, are what were mapped as streams and rivers. The blue, that's sometimes hard to see, is what they mapped as a connector, and then this orange is what's called an artificial path. And just look at the arbitrary nature. Here, this is called a connector, but this is an arbitrary path. It all looks the exact same to me, and it looks just the same as the stream that's downstream from there. So here we're getting very detailed information, more detailed, I would say, than the lake body. Oh, and you can see it just ends. So is it flowing down this way, or does it originate there? But it also ends just here. So this is maybe a very flat landscape where maybe this isn't a stream at all. It's just a very low area that doesn't have a lot of flow to it, and maybe wildlife are making these paths. It's hard to say, but here we're given almost a false sense of precision in our data because the streamline is being mapped in different descriptors, and yet is that true precision? And as carefully as the stream channel has been designated, it doesn't actually follow the path of the stream very carefully. So again, healthy skepticism. Think about the data. Okay, we can't make a one-to-one map. That would be impossible. We would end up with a drawing that would be the exact same size of the world, or a digital representation that would be the exact same size. So some details are going to get dropped, and in comes the uncertainty. Whenever we make some kind of simplification, we are decreasing precision and accuracy and increasing uncertainty. So the one making the map and doing the analysis is the one who has to make those decisions about whether or not to account for them and acknowledge them, Or even if it's you collecting the data, are you going to write it down and include a metadata file that talks about how you went about simplifying and the assumptions that you are making with the data? So, we have to throw away or ignore some non-essential information. We're going to lose detail, but that allows us to cover broader areas and make larger extent data sets. And then we have to think about if we're going to map in discrete manner, right, where we actually draw outlines of things or center lines of roads, or use continuous fields, something like an aerial photograph like this. I think we're all a little bit spoiled by high resolution and our streaming speeds and megapixels, and we very quickly come to expect precision in our data. This is just the world that we live in now. But spatial data has a long and relatively ugly history. A large chunk of it, stuff that we use every single day, was created using very archaic methods like tracing paper maps, really. So be curious and skeptical about the lineage of your data. Where did it come from? How is it created? What scale is appropriate for your analysis? Why is it important to understand scale and detail? Because it's going to limit the analyses you can perform. It's going to limit the information that you can extract. And when you combine data sets of different scale, the coarsest resolution is going to limit the precision of your results. All right, so here it is, 2 fundamental models for storing geographic data. Vectors, which are based on specific coordinate locations and can store information about each location. And rasters, which are a matrix of cells that cover a whole area. So in this course, we're going to be primarily using single band rasters, which means that each cell or pixel stores one value. Understanding these data models is, again, one of 3 fundamental things that you need to know to do intelligent GIS work. Data models, defining locations accurately, and understanding the limitations of spatial data. The 4th thing we're going to concentrate on this semester is professional communication of your results so that the world knows you're doing intelligent GIS work. Okay, so whether vector or raster, small scale and coarse detail, or large scale and incredible detail, we can stack or layer maps containing different data models and contain different geometry and information to create better understandings of a place. Each one of these maps is showing Logan and the entrance to Logan Canyon. It's the same spatial extent and scale, but the data sets have different levels of detail and represent the landscape differently. We'll stop there and we'll pick up with a little bit more nuance about vector data.